Boom. All right, Julie Bender takes us to the last chapter of today's work, and that is Kirchoff's principle or Kirchoff's role and complex circuits. Yeah, this is an amazing chapter. Remember, the former chapter was current electricity. Now we are at the last chapter of my own part of the job, and current complex circuits is a very simple area. All you need is just understanding, okay? All right, let's go into it. Kirchoff. Kirchoff extended the works of Simon George Ohms, into an explicit way of calculating current in networks of circuits. And this he achieved by introducing two rules. Number one, the junction rule, and number two, the loop rule. If you understand these two rules accordingly, then you will have little or no problem as far as Kirchhoff's works are concerned. Right? Good. Let's start with junction rule. According to Kirchhoff, right? Junction rule says that the total sum of the current entering a junction is equal to the sum of the current leaving the same junction. Yes, this, however, is in line with the law of conservation of energy. Yes, it's in line with the law of conservation of energy. Now, take note, he went further to say that the current entering a junction is positively charged, while a current leaving a junction is negatively charged. And by the time you find the algebraic sum of the positive and negative of current in a junction, it will always give you 0. That is the junction rule. So you can draw different diagrams and then calculate the missing current and also ask for direction. If in the process of calculating you have a negative current, know that it is leaving. If you have a positive current, know that it is entering the junction. Okay? Now that takes us to loop rule. According to Kirchhoff, the sum of the potential difference across all the elements in a closed circuit is equal to 0. The potential difference across all the elements, which are the resistors in a closed circuit, is equal to 0. Not just resistors, and EMF as well is equal to 0. Now, this is achieved through a clockwise or an anti-clockwise movement, taking into consideration the direction of the current in the existing circuits. And that is to say, if you are taking a clockwise direction, and your clockwise direction happens to be in the same direction with current in the circuit through a resistor, then potential difference will drop. In other words, because it is in the same direction, your potential difference is negative. If, however, the clockwise or the anti-clockwise direction you are taking is in this opposite direction to the existing current in the circuit through a resistor, then potential difference will increase. And when it increases, potential difference becomes positive. So you have to be very careful with this. Same direction, negative, opposite direction, positive. Now, what if your direction of clockwise or anti-clockwise is going through the EMF of a cell? The EMF of every cell is made up of positive and negative terminal. The longest stroke is positive, the short one is negative. So if you are moving from the positive terminal to the negative terminal of a cell, then the resulting EMF is negative. If you are moving from the negative terminal to the positive terminal as a result of your clockwise or anti-clockwise direction, the resulting EMF is positive. You get it? Good. So you have multiple diagrams like that which you can play with. So questions will always come and they will just give you a circuit diagram, and the next thing they will ask is to calculate the current flowing through the system. And that means you have to first of all state your junction rule. Thereafter, you state your loop rule. And of course, your loop rule depends on the number of loops you find in the circuit. And then from there, you solve them simultaneously and calculate the values of I1, I2, I3 as the case may be. And if you are asked to calculate the potential difference at a given particular position, if they say calculate the potential difference between point A and B, that means you either go clockwise or anti-clockwise. But if they say A and B, they have given you direction already. So it's already clockwise. So for you to do that, you're moving from the negative terminal to the positive or positive to negative, depending on the circuit diagram. And then you can get the potential difference across that just like that. So that takes us to potential dividers. Now, potential dividers are very suitable device meant to determine voltage across a given load. If you want to find out the amount of voltage across a particular resistor, you make use of a potential divider, aka PD. There are 3 types of potential dividers. Number 1, you have the fixed potential divider. Number 2, you have the variable potential divider. And then number 3, variable without load potential divider. Then number 3, variable with load potential divider. So we start with the very first one there, which is the fixed potential divider. A fixed potential divider consists of a source of voltage, which is V0, that powers the entire circuit, with two resistors R1 and R2 arranged in series. So you can calculate the potential difference across R1 or calculate the potential difference across R2. But for you to do that, you first of all need to determine the current flowing through the circuit. And the current flowing through the circuit, according to Ohm's law, is V over R. V is the voltage of the circuit, V0. Then R is the effective resistance of the entire circuit. Because the two resistors are arranged in series, the effective resistance is simply the algebraic sum, which is R1 plus R2, right? Good. Now that I have the current as V0 all over R1 plus R2, the next thing I have to do is to calculate the voltage across the R1 resistor. And that becomes the voltage, which is V, equals to the current in the system times the resistor of R1. So the voltage across the R1 resistor now becomes the current in the system V0 all over R1 plus R2 times R1. If I am calculating the voltage across the R2 resistor, then it becomes the current in the circuit times the R2 resistor, right? Now let's go to variable without load potential divider. This still consists of a voltage supplier V0, and then here you have a single resistor that has variability in grading. As you are moving from one place to another, you are varying the capacitance of the resistor. Okay, so you can either tap it midway, you can tap it 1/4 way, 3/4 way, depending on the examiner. So what we are saying now is, if you want to calculate the potential difference across a given part of that variable resistor, maybe halfway or maybe 1/4 way, then all you need to do is to first of all identify your R1 and your R2 based on the information given. If the information says that it is midway, then R1 is equal to R2. If it is 1/3 of the other, you know what your R1 and your R2 is going to be. But at the bottom line is that for you to calculate the potential difference across any of the resistors, it is the current flowing through the circuit times the resistor in question, right? Good. So next one there is the potential divider, that is a variable potential divider with load. Now this one also consists of a source, but this time around with one variable resistor and one fixed resistor. The variable resistor is connected to a fixed resistor such that at the bottom they are in parallel, while the one at the top is more or less like separated from the parallel arrangement. So if you resolve the parallel arrangement, you now add it to get the series arrangement. You get it? Good. Now, if you're asked to calculate the current across the R3 resistor, you know what to do. First, you have to find the current in the circuit, and that is the voltage supplier, which is V0 all over the R effective. Now, because there are three resistors, the R effective, first you deal with the parallel arrangement. Once you're done with the parallel arrangement, you can now focus on the series. So parallel becomes R1 R3 divided by R1 plus R3 plus R2. That's R effective. So by the time you are able to get that R effective divided by the source of voltage, that will give you the current in the system. So with that current in the system, you can calculate the potential difference across any resistor. If it is across the R3 resistor, multiply by the current. If it is across R2, multiply by the current. If it's across R1, multiply by the current in the circuit. However, some cases will come and you're asked to calculate the potential difference across two resistors. And that will be the one in parallel. And you know what to do. For them to be in parallel, you have to find their effective resistance. So that becomes R1, R2 all over R3 plus R1. So that will now serve as the resistor that you will multiply with the current flowing through the circuit. And the same thing will happen if they say across R1 and R2 that are in series. That one becomes the algebraic sum in product with the current flowing through the circuit. And that is what you need to know about potential dividers. Now that takes us to the next part of it, which is the slide wire potentiometer. Now, this is an experimental setup to measure the potential difference across two terminals. the potential difference across two terminals of a circuit with high accuracy, with high current accuracy from the source of measurement. A potentiometer consists of a high resistant wire of length 100 centimeters connected to a battery of known EMF. The positive end of the known battery is connected to the positive end of the unknown battery. The capacity of the known battery is always higher than the capacity of the unknown battery. Then, the negative terminals of the unknown battery is connected to a galvanometer and then to a jockey where it taps on the resistant wire. Now, take note, the function of the galvanometer here is to detect any little amount of current. Now, as the jockey is being tapped from one part of the resistant wire to another, there comes a point where you tap and there will be no more deflection on the galvanometer. That point is referred to as balance point. And at balance point, there is no deflection, no current flows through the galvanometer. And when that happens, three things happen at balance point. Number one, no current flows through the galvanometer. Number two, the voltage of the known EMF will drop to the voltage of the unknown EMF, and that will help you detect that EMF. Then the third thing that will happen at balance point is that the EMF becomes directly proportional to the length of the wire, which is the resistant wire. That's the gospel truth. So at the end of the day, you will have E1L2 equals to E2L1. You get a message? Good. Now take note, when you tap that jockey at point 0, the EMF of the known cell will read 0. If you tap it midway, the EMF of the known cell will read half of its value. If you tap it at the 100 cm mark, it will read its full value, which is 12 volts. So in the process of tapping, there will come a point where you will tap and the voltage of the known cell will become equal to the unknown. Then there will be no deflection, and that is called balance point. Now that takes us to Weston bridge. Weston bridge is an instrument used to measure accurately resistance of wires or resistors, as the case may be. And these resistors are usually arranged in a four-corner diagonal way: R1, R2, R3, R4. R4 can be RX, okay? Then you have a galvanometer in between with a jockey, or let's say with a key in between, so that once current flows through the circuit at balance point, where no current is flowing through the galvanometer, the resistance of the resistor up becomes equal to the one below, while the resistance of the one on the right hand side up becomes equal to the one below. And that simply means that R1 over R2 becomes equal to R3 over Rx. And with that, you can calculate the value of Rx, right? Good. So that is that for the Weston bridge. Now we go into the last one, which is the slide wire bridge. The slide wire bridge is an applied version of the meter bridge, which is the potentiometer, or you call it Weston bridge as the case may be. It is aimed at accurately measuring the resistance in a circuit. It comprises of a thick copper wire or brass wire of 1 meter length connected to two resistors, one with a known value of R while the other with an unknown value of R. So you are using it to measure resistor now. So it's more or less like an applied version of the potentiometer. Now, when a galvanometer is connected, then a galvanometer is connected in between the resistance, as you see here, and you have a jockey which you can use to tap on the resistant wire. Now, at balance point, when no current flows through the galvanometer, what happens is that the potential difference across the two resistors becomes equal to their individual lengths below. What do I mean? At balance point, the resistor on the left-hand side becomes directly proportional, or let me put it this way, the resistor on the left-hand side all over the length below it is equal to the resistor on the right-hand side all over the length below it. So, if the length below the first resistor on the left-hand side, which is X, is equal to L1, while the length on the one below R is equal to, At L2 now will become 100 minus L1, isn't it? Good. So from there, you will be able to hypothesize the value of X. You know, this does not work like potentiometer where at balance point voltage drops. Here there is no resistance dropping. All you need to know is that X up equals the length below, R up equals the length below, and then from there you sort out yourself by making that the subject of the formula. Wow, ladies and gentlemen, we have gotten to the end of this course. Yeah, I'm only teaching 8 chapters, so this is the end of chapter 8. It wasn't easy to get this done, and we thank God that it is complete. Thank you for listening, Jolly-Ben. God bless you with a retentive memory, and make you the best, and make sure that all your dreams are achieved. Through Christ our Lord. Amen. Boom.